excuse me, not positive. You only can take logs of positive numbers unless we're doing imaginary numbers. We don't do that in this class. So log of a number bigger than 1, right, is positive. So this thing is positive for bigger V2 than V1, which is our physical situation. However, I left the minus sign in here and left these guys as they are. So this whole thing then, because temperature is absolute temperature, it's got to be a positive number, and it's got to be a positive number, positive. This whole thing is negative. Good. As it should be. The answer is less than 0, right, as we know it had to be for this situation. So I got my signs right. Miracles, miracles. But if I got the answer wrong now, if I check the sign was wrong, I'd go back and find my minus sign error. But I didn't. I think I got it right. Or if I did, I made 2 minus sign errors. That's what happened. Anyway, always make an even number of negative sign errors. Or if you multiply by 2, just make sure to divide by 2 somewhere else. You know this? You know the Feynman sign rule? So Richard Feynman is a. Well, I think I should make such claims. But yeah, after Einstein in the U.S., most famous, and Landau maybe okay. But Einstein's pretty famous important scientist. The Feynman sign rule was that if the sign is wrong, change it. That if you follow that rule on the exam, on the final, you can lose points if you just change it willy-nilly at the end. So Feynman would have been docked points for following his rule in an 8A final. If you find the sign is wrong at the end, go back and find where the mistake was. And you can even note if you're sure it's wrong, you don't have time to find it. Like what you should really do is find it and correct everything so it's all self-consistent in the signs right in the end. Not because you just changed it at the end. But if you notice at the end that it's wrong and you're out of time, you can leave a note to the grader saying, I don't believe the sign is my answer for this physical reason, but I don't have time to find where and you might get a break as a result of that. But if you just change signs willy-nilly at the end because you know it's wrong, it can actually hurt you because they can't see where it is. So Feynman, yeah, he was a very smart man, but not the way to handle it on the finals to change it. Although it's good to notice if signs are wrong. Okay, good. So that's isothermal. We solved for work. Now let's solve the rest of it. So what is the change in the energy for an isothermal process? So first of all, what's the change in temperature? What's delta T for this process up here? 0. You bet. That's how we started this whole thing off, right? I don't know what the temperature is, and I can calculate it, but the change in the temperature has to be 0. That tells us right away that the change in energy has to be what? If the temperature of the gas didn't change, then because energy equals 3 halves NKT, right? It's got to be 0. So that's why this is a special process. It's a process where the energy doesn't change. It's also special because it's easy to put things in thermal equilibrium with a heat bath. Oh yeah, what's that? So we know that because I stated at the beginning, I'm specifically interested in the case of constant temperature. We are like what are we doing right now? We're computing all these changes and how much work was done and how much heat was exchanged and what was the energy change for an isothermal process. That's where I started. So at the very beginning of the problem, I write down delta T equals 0. So I could have just written delta T equals 0 at the top and said, okay, temperature's not changing. And not only is it not going to be different from in the endpoints, not only are the endpoints at the same temperature, every point along that curve is at the same temperature. In other words, just like I talked about there, how you don't have to go straight down to get from point 1 to point 2, you can take some other path if you want, but if you do that, the work is different, the heat exchange is different, all that. In this case, the specific path we're taking is one that, for which every point along the path, temperature is the same, right? That's why when we took our integral for work, we followed along a path that had, I was able to pull temperature out of the integral because it's constant. It doesn't depend on the volume. So when I integrate over volume, I can just pull it out as a constant. So temperature is constant. We know that for this particular path. Because of that, we know that for this special path, the energy change is also going to be 0. And that tells us immediately then what the heat exchange has to be, right? Because by the second law, the first law of thermo, right? I know that Q in equals delta E minus work on. Well, delta E is equal to 0. So that means that Q in just equals negative work on, right? Whatever work was done, and exactly the opposite amount of heat was exchanged in order to keep things at the same energy inside the gas, right? And so what is that? It's negative work on. Well, work on is actually a negative number. So now I get a positive number, NKT times the log of the ratio of the big volume over the small volume, right? So that's my heat exchange. All right? So I'm doing the same old thing over and over 3 times in a row now, but just for different physical situations. I explicitly calculate the work. I explicitly calculate the energy. In this case, it was easy, the energy change, right? The other cases, I had to do it by looking at what the temperatures were, the energies were at the 2 endpoints. And then I figured out the missing piece. I figured out what the heat exchange had to be to achieve that. Let's see. So, let's see. Anything else I want to say about that before I can look at my notes here? Okay, so that's 3 very important cases. There's a 4th case that's also very important. I'm not going to go through as much of the math because the math is a little bit less pretty, but I'm going to give you the end result, and we're going to think through what's going on. And it's this case over here. I showed you this demo last time, but I like this demo so much, I'm going to do it again. I like this demo. Yeah, so I can burn something. All right, so I've got this. So what am I doing? I've got my fire syringe. I think most of you saw this at the end of last lecture. I'll do it one more time for those of you who had already escaped. So this is just a piston. Just got oxygen and nitrogen, O2 and N2. So it's okay, fine, diatomic, it's fine. Nearly an ideal gas, right? And I'm gonna excuse me, it is an ideal. Well, yeah, it's nearly ideal and it's diatomic instead of monatomic. But when I do the equations, I'll do it for a monatomic gas. And what I'm doing is, if I can get maybe I can't get in there. Right, it worked last time. There we go. That's a little stiff today. Yes, it worked really well last time. We'll see if it works again. Here's the idea. This is not about friction, even though you saw me struggling to get this thing inside here. Many students, when they first see this demo, think, oh yeah, friction. You move this thing in, and it rubbed against the wall, heated up, and then that piece of paper burned up. That's not what's going on here. In fact, there's no heat exchange here either. What I'm going to do is demonstrate a process called an adiabatic process. Adiabatic is one of these nasty physics words. It actually means different things in different contexts. It's terrible. Adiabatic can either mean really slow or it can mean really fast. So I don't even use the term. I like to say instead, it's a process that involves no heat exchange. I'm going to push the plunger down really fast. And it's important that it's fast. If I go really slowly, then there will be enough time for heat to be exchanged with the outside world. So there's 2 things I can do to prevent heat exchange from occurring. One is I can insulate this thing, and we've done that. You can see that there's an outer cylinder and an inner cylinder inside there. I've insulated it. There's a second thing I've done, which is I'm going to move really fast. When you move really quickly, there's some time it takes, right? We went through those equations before about thermal conductivity, and, actually, we worked out the time aspect. I don't remember if we did that. But we did talk about, I guess we did. We talked about the flow rate, how much time it takes for heat to transfer. Well, if you have a lot of insulator there, it's going to take longer for the same amount of heat to be exchanged. If I move really quickly, then I can do work on the system. And that's what I'm doing. I'm pushing this thing down, force times distance, right? I'm doing positive work on the system. I can do work on the system very quickly. There's no time for a heat to be exchanged, so Q will be 0. But the result will be that the energy inside the gas must go up. In fact, it's got to go up by more than it would if I moved along a constant temperature path. So I'll do it real quick and we'll see what happens. We're going to go up to, what is it, 451? At least 451 Fahrenheit, because that paper's going to burst into flames if I do this right. Okay, so we'll go 1, 2, 3, and I'll do it. So 1, 2, 3. Oh yeah, it worked like crazy, just like last time. I love that. That's such an effective demo, and I'm really shocked that it works that well because it's weird. I can do work and heat up a gas. In fact, let's think through what's happening. There's gas in there. Molecules are bouncing around. I'm not lighting a flame under it. I'm not heating it up by adding heat, right? But what am I doing? I'm moving a piston. I'm moving the plunger inside the cylinder, right? And the piston inside the cylinder. The result is that when a molecule is coming up at some speed, it bounces off a moving wall, right? And it bounces away faster than it came in, right? In fact, it bounces away with an extra velocity that's twice as much as the velocity I'm moving. This thing is infinitely massive compared to those little tiny gas molecules, right? So they don't have, it's like, they bounce against that wall and they bounce off. Let's say it's an elastic collision, in comes this molecule, right, at some velocity, v initial, right? I come down at u, let's say, right? So what happens is, bang, right? He bounces away at with a speed that's equal to his initial speed v plus 2u. If I got my numbers right. I think I did that right. I think that's right. In fact, if I think about what it's like from the center of mass coordinate system, well, this thing's infinitely massive. This thing coming down compared to the molecule. So from the coordinate system of the center of mass, I just move with this infinitely massive thing because it's dominating the center of mass, right? The mass from this little molecule is nothing. So if I watch it from this standpoint, he bounces away with the same speed as he came in at in that reference frame. So that's where I get that 2u from transferring back and forth between the. Anyway, if that was helpful to people, the bottom line is that I hit like a baseball bat. I hit that thing and speed it up. You might say, well, so what? You weren't moving that fast. I mean, like, these molecules are moving super fast, right? I was moving. I was as fast as I could go, and I spent a lot of time, working on my speed. But come on, that wasn't that fast. But the reason it has a big effect and can heat it up so much as to get the fire to burn, get the paper to burn, is that the molecules, first of all, many of them bounce against this thing, but also each individual molecule bounces against it lots and lots of times. They're going super fast in there, right? And every time they rebound back and come up and meet against that moving massive object that's coming down at them, they get boosted up a little bit. They get a little more increase in their velocity, in their speed. I should say speed, not velocity. It's changing the direction of velocity and increasing their speed a little bit. So the result is that they get sped up many, 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 many times. And eventually, they're all sped up so much that the temperature has gone way up. There's no way for the heat to escape. I'm doing it too quickly, and it's insulated. And the result is the temperature goes up, the energy goes up, and we get above the flash point, and the paper burns. So what does that look like on a PV diagram? Well, it looks like this. I wonder if I should use the same board. Maybe I'll draw it a little bigger. Let's do it over here, Nick. Let's get a bigger picture. I haven't been using my big system over here so much, but all right. So let's draw a picture of this. And this is I'm going to put it in quotes, adiabatic. It's an adiabatic process, but really it's Q equals 0. That's what it is. That's what I'm talking about. No heat is allowed to be exchanged as the gas expands. Or in this case, it wasn't an expansion. I compressed the gas. It was an adiabatic compression. It was a constant. It was a no heat exchange compression. I didn't put in or out right here because it doesn't matter. If Q in equals 0, Q out equals 0. I'll go ahead and put it semantic, but it doesn't matter. It's 0. So what does that look like? Well, let's do our PV diagram. We started off at a point that's with a big volume, right? So here's our V1 way out here. And then we went this way. Well, let's say that we moved at a constant temperature. Suppose the temperature didn't change, right? What would that look like? Well, that would be like one of these isotherms, right? This constant temperature line. So this thing is constant T, right? But that's not what we did. What I did was, because remember, from our picture up here, when we move along a constant temperature curve on these isotherms, heat is exchanged, and we calculate it, right? We calculate it right here to be, well, in the case of an expansion, we calculate it to be a positive nkt log of V2 over V1, right? But in fact, we're doing a compression now. So we can just turn all this around, just change the signs of everything, make your arrow go the other way if you're isotherm. If we did an isothermal compression, right, then Q in would be negative nkt log of V2 over V1. That's a negative number. That means that heat came out. So if you compress a gas slowly and have it in thermal contact, with a reservoir, a heat reservoir, okay, then what happens is heat comes out as you compress it. You're compressing it, you're doing work on the gas, you're adding energy by doing work on it, but the temperature's not changing in the gas if you go really slowly and it's in contact with a heat reservoir at that same temperature, like the room, right? So what happens is heat has to come out, right? You compress the gas, you're doing positive work on it, but there's negative Q in, meaning there's positive heat leaving, and the result is the energy in the gas doesn't change, all right? And that's what we found here too for isothermal, delta E is 0. So now what we're doing is we're compressing it and we're not letting the heat escape. We're adding energy to the system and we're not letting the energy get out. So does that mean that as I go to the left, as I compress the gas, thinking now about this really fast compression where Q equals 0, are we going to be above this curve or below this curve as we go to the left? Above, because this is hot up here, this is hot, this is cold, right? If I compress it quickly and the heat can't get out, well, if the heat could get out, go along here. If the heat can't get out, it's going to get hot. And we saw that's why paper burned. The temperature went up, right? Because the energy in the gas went up, had nowhere to go. It couldn't get out in the form of heat. So that's what it looks like. It does this. That's right. So that's my adiabatic compression to go from this point to that point. So this is what I will call V2. See that? And then once again, you've got our V1, you've got our V2. Let's see. Oh, did I get backwards? Oh, yeah, you're right. Mix up my P's and D's. So easy to do. I got my subscripts right. I got the name anyway. All right. So good. I think I drew it correctly now. And that's qualitatively, that's good to understand. That's what happened when I compressed quickly. Right? Now, this is still, let me make it really clear, it's sort of surprising maybe, that everything we're talking about so far is a reversible process. Well, this too is a reversible process. And what do I mean by reversible? I mean exactly what that says. I could do it in reverse and get back to where I started. Now, for that to be true, it means that the system always has to be in thermal equilibrium the whole time with itself. It has to have a well-defined pressure, volume, temperature. And that's pretty much true over here. Even though I was moving quickly, I was moving pretty quickly, but as long as the gas is able to equilibrate as I add energy. Like if I move so fast that the air was building up around if I'm moving at the speed of sound or something like that, okay, well maybe that's not going to be reversible. Maybe I'm right. But I'm not moving that fast. I'm just making sure that I'm moving fast enough and I'm overcoming the time scale that's needed for the heat to have escaped through the insulation that's there. Just fast compared to that, but not so fast that that different parts of the box have different concentrations of gas molecules or something, right? Or that the temperature is somehow different in different places, or right? Then we're leaving the realm of equilibrium. So we're assuming that we're in equilibrium everywhere along the way, and that's why I'm allowed to draw a curve on this plot. If I did something that took us out of equilibrium, I wouldn't be allowed to make a curve along here. I have a well-defined endpoint, I have a well-defined starting point, but the intermediate points may not correspond to a thermodynamic system that's got well-defined P and a V and a T and an N, right? I mean, well, I guess N's not going to change, the gas molecules aren't escaping, but the other things might all be ill-defined. So what's important here is that I'm moving fast enough so that the energy that the heat can't escape, but I'm going slow enough that I'm always in thermal equilibrium. Okay? Great. All right, so let's see. So in terms of calculating things from this, well, we can go ahead and think about the work as the area under the curve. It turns out it's not horrific, but it's more than I want to go through in lecture, and I don't want you to focus on that so much. But I do want to think about, let's do calculate the change in the energy. The energy, again, the energy is a state variable. It only depends on the endpoints. So even with something complicated like this, we're able to talk about change in energy if all we have is information about the endpoint. So what does that look like? Well, it's going to equal work on, right? Because by the first law of thermodynamics, like this thing is 0. So that means that, well, this is the first law of thermo. Here, plus Q in, and that's 0. So good. It's equal to work on. What does that equal? Well, it equals the change in the energy. Let's just go ahead and calculate that. Actually, am I going to calculate it from, I think I'm just going to assert to you That's what it is. Is that right? Oh no, actually we can do it, right? We know the change in energy is because of the endpoint. No, but right, I can't calculate the okay, forget it. I'll just go ahead and tell you what it is. It's P2 V2 minus P1 V1. Okay, there we go. Oh, and notice this is the first case we've seen of all these formulas where I've got where P1 and V2 are both appearing in a difference like this. For those two first cases we had a delta P times V or a delta V, whichever way I said it the other way around, delta P times V or a delta V times P. In this case we don't have that. We have P2 V2 P1 V1 because they're distinct, right? And where does this come from? So this is assuming a monatomic ideal gas. For other types of ideal gases, diatomic, so on, right? You can get different factors here. So this depends on, I just went ahead and struck the formula. So the book gives you more general formulas. It talks about the specific heats of gases, how that depends on monatomic, diatomic, all this stuff. I'm just going to go ahead and assume it's monatomic. Okay, so that's where that comes in. I think the formula is the same, otherwise you just get different constants in front. Okay, great. So now we know what all those things are, what all those differences are. Oh, actually, yeah, I guess what I said before, I kept hesitating about this. So this, of course, is just calculating the delta E the straightforward way. The thing is, though, I haven't told you how to calculate what this is based on this. You don't. So the problem description tells you what V2 is, what V1 are. If you know what P1, P2, V2, and V1 are, then you're golden. You just plug stuff in, that's fine. You just change the energy. If you only know what V1 is and you're trying to calculate what this thing turns out to be, then you need to know more. And that's what I'm not going into details about. Okay, that's where I decided to draw the line. Again, this is still reversible. And it's let's see. I also want to say about this before I move on to the next interesting case, which actually is not reversible. But this is reversible. Let's see, we got the work. You know, same rules as before. You go to the left, it means work on the system is positive. If it goes to the right, work on the system is negative. So this happens to be a positive work. And in fact, let's check if I got that right. The change in energy for this process, it better be positive, right? Because I did work on the system, but no heat exchanged. So let's see, P2, V2, P2 times V2. Are those, that's an interesting question. Is this actually being a positive number or not? Well, let's check. So we know that if this were where I wound up for the isothermal process, then if this were P2 and V2 were over here, then P2 times V2 would equal P1 times V1, right? After all, the energy didn't change for an isothermal process. If we go more steeply, though, then V2 is bigger than it would have been if it were isothermal. That means that this first term is bigger than what you would have had for an isothermal process, and this term is unchanged. So sure enough, a bigger positive number, good, you get a positive answer. So this thing does give a positive delta E, and that's specific. That depends on the fact that we're compressing. If I went the other way, if I did a quick expansion, adiabatic expansion, where no heat or one with good insulation, so no heat is exchanged, in that case, give a minus sign in front of the whole thing, so the energy change would be negative. And again, it would be like this. If you started over here, you'd wind up down here someplace, right? Instead of making it all the way over here. All right. So what's that other case I wanted to bring up? And do I want to mention it before or after I talk about? I think I want to talk about it after I talk about engines. So everything so far has been, so first of all, everything's reversible, we've talked about so far. And we've really been focusing on the gas itself, not the things that are acting on the gas, the heat reservoirs in contact with, all that kind of stuff. It's really important to keep straight. What system are we talking about, right? So one thing we can ask, I think I've mentioned it several times, but I'll just make an explicit statement about it, is that the way you build, the way you build an engine, right, is have something that goes through a cycle in the PV diagram, right? So it's a huge discovery, whatever, in the 19th century, right, that they could build these things. And what does it look like? Well, any cycle will do as far as producing useful work in exchange for adding heat to a heat engine, as long as it's going clockwise. So let's think through what I mean by that. If we think about what's going on, if I have supposed to have some closed path, whatever, I'm just going to choose some funny path, whatever it is. So I have some closed path like that, clockwise, in the PV diagram, for some gas in a piston, whatever it is. What does that mean? Well, first of all, there's work being done through one cycle. So a cycle, I just mean let's start right here at point 1, and then we'll go around. Actually, let's choose 1 to be really convenient. Let's make it as far over to the left as we can make it. So let's call this point 1, and let's call this point 2, right? So if we do that, now we've got two curves that are just going left to right or right to left, right? And if we consider this curve first, it's going from 1 to 2. In that case, we get some amount of work. So work on for a cycle, right, equals work on from 1 to 2 plus work on from 2 back to 1 again, right? We can just add up the work individually that's done on the gas in both cases. And I mean, are we going to do work on or work by? Let's do work on to be consistent with my. Let's see what I was doing. Let's do on here and on here. Good. I think that's what I wanted to write. So what does that look like? If I draw the same picture here and then draw just that top part, say, okay, here's 1, here's 2, right? Now we get this area under the curve. That's the work we did. And is it positive or negative? Well, if I'm going to the right, work on is a negative number. So that thing is a negative number. Less than 0, right? And this side, what happens? Now we make our PV diagram, and we go from 2 back to 1. But notice, since we're going clockwise, this curve is lower than the first one, right? So going back this way, now when we calculate how much work is done, we have a smaller area under the curve, right? So this is a smaller number than this is. This one's positive and that one's negative, so the net result is that work on for a cycle is going to be a negative number. It won't be 0. So that's another manifestation of the fact that work is not a state variable greater than 0. Right. And let's see, work on 1 to 2, what if we decide that the absolute value of this, right, is greater than the absolute value of work on 2 back to 1 again, right? In other words, this thing does net negative work on, which means it does positive